mu. So the only reason we use mu the static friction coefficient is because, we're trying to find it where it's at the max speed where it doesn't slip.
Right.
If the problem said, what would a problem ask where we're trying to find mu sub k? Or like the.
No, I've never done a mu sub k on a problem like this,
Okay.
just. No, I don't think I have. It gets just overly complicated.
Okay.
Probably the more complicated one would be, with friction, what is the minimum angle so it doesn't slip? Or what is the maximum angle so it doesn't slip?
Okay.
And if it were the minimum angle, it would be slipping up on the curve, on the,
It would want to slide up the curve, yeah. So this is basically the exact same setup.
right, okay.
Now, if we had it, so what is the maximum angle so it doesn't slip? So in other words, the car wants to slide down the ramp, so friction's acting the other way.
Yeah.
What would change is the friction would now be in those directions. That becomes positive, that becomes negative, and then everything else, you just continue propagating the change in sign.
And we could still assume that friction is perpendicular to y cosine theta and y sine theta, right? So we don't have to break
Right,
it up.
oh yeah, yeah. Friction better be perpendicular to the normal force.
Yeah.
All right, there's one other thing that I want to hit, and I recognize we are low on time, so I'm gonna jump into things that we've already done. So we have centrifugal acceleration, the magnitude is v squared over r. We've also talked about, when we were doing the derivation of that s is equal to r theta, that the arc length is equal to the radius times the angle in radians. So the change in length is equal to r times the change in angle, which in essence means the exact same thing as we just did. It takes a certain amount of time to do it. So if you divide by time, we basically have a distance over time, which is speed. And then this delta theta over delta t is a change in angle over change in time. This is angular speed. Omega. So we have a relationship here between speed and angular speed. So imagine that we were outside, we all held hands, we have somebody in the middle, but we're all maintaining a straight line, and the person in the middle just starts moving slowly. The farther out you are, we all want to rotate at the exact same angular speed, in other words, go through the exact same angle in the same amount of time. So if R goes bigger, V gets bigger. So as we turn, the person on the outside is gonna have to be running at some point, whereas the person in the middle doesn't have to move very much. If we make that substitution in here, we get r squared omega squared over r, because v is equal to r omega. One of the r's cancels out, and you're left with r omega squared, or I think as I wrote on the lab, omega squared r. Anyway, that's where it comes from. Omega is the angular speed, so in the lab, if you know how much time it takes to go around once, in other words, the period, that's the time it takes to do one cycle of repetitive motion. And so if we're talking about something going around and ending in a circle, then the angular speed is 2 pi divided by that period. That's for one revolution.
Will we always use radians when it comes to, centripetal, like, well, I guess motion?
Generally, when I give you an angle of a physical angle like that, I'm going to give it to you in degrees.
Okay.
We typically use radians for cyclical motion,
Yeah.
so we're going to be dealing more with radians when we start dealing with angular speed, things like that.
What I'm saying is the omega equals 2 pi over t, will it always be 2 pi or will it ever be 360? Cause isn't the
It-
period measured in radians?
You could do 360 degrees and end up with degrees per second, but,
Yeah.
and for practical reasons, I've never done that. Degrees per second is just awkward.
Okay,
Probably the other alternative, radians per second is typical, those are international standards. Revolutions per minute or revolutions per second is another way of expressing it. That's generally the ultimate unit
okay.
that we use.